Now, one of the things that you'll feel as we go through today is you'll say, this has almost nothing to do with last time. And last time, what were we talking about? We were talking about these line integrals. And we're saying, well, let's find what happens as we integrate along the line. We can think of it as we have this surface up in three-dimensional space. And we said, well, how much area is there between the surface and a curve in the plane? That's how we sort of introduced line integrals. Then we got into the problem of work. And today, we're not going to talk about any of that. So you're going to feel like there's no connection. But come next time, because we're going to tie the two together. And you're going to say, ooh, that's nice. So, what's today? Well, today we're going to talk a little bit about vector-valued functions. But what we're really trying to build up to, and this is sort of a foreshadowing of the rest of the class, is to say, what about this thing called vector calculus? And of course, if we're going to talk about calculus, we need to be able to do two things. And calculus is the idea of there's these two beautiful questions. How are things changing, and what's the total? And the fundamental theorem of calculus is what ties these together. And so we want to talk about vector-valued functions, and we want to talk about things where we can start to ask these questions. Now, we're going to start with functions. We know what functions are. We've seen this before. Most of the functions we think of are the case where we have a number or possibly several numbers. We plug them into some sort of machinery. And once that machinery it goes through, does whatever it does with it, out comes a number. Okay. So when we say the input, it could be, say, a single variable x, or it might be several variables, x and y. And the output is a value. Vector-valued functions are very similar. Now, the only thing that changes for vector-valued functions is what kind of thing comes out of the machine. So here, a vector-valued indicates that the output is a vector. So the difference between scalar-valued and vector-valued is what's coming out of the machine. So again, we put in some numbers, possibly a single number, run it through a machine, out comes a vector. Now, we've seen these before. So in some sense, we're kind of familiar with vector-valued functions. So as an example of something that's a vector-valued function, we said, well, we can model motion. So we can have our pieces be x of t, y of t, z of t. And in that case, what we had is we put in a single number, a parameter which we thought of as time t, and the output is something related to where we're at. And then we could start to do things with that, such as take derivatives and so forth and so on. But another case which we saw was also when we talked about the gradient. So in this case, we had the output were partial derivatives at a location. We said, oh, that gradient, that's giving us information for the local behavior of the function. And this is a case where we put in two numbers, x and y, out comes a vector, and then we can get things such as what does the tangent plane look like, and so forth and so on. Now, one of the things we like to be able to do with vector-valued functions is try to visualize them, try to understand them a little bit more. Now, how can we go about doing that? Well, with numbers, when we go back to our old function, it was kind of easy. We said, all right, if I want to graph a function, I have my x-axis, and then what I have is an extra dimension, which we call y, and at every single point on the x-axis, we said, what's the height? So we plotted all these points. And after we plotted all the points, then we saw this curve, and we called, oh, that curve is the function. Well, more accurate, it's the representation of a function. We can do the same thing, of course, in three dimensions, where we have two inputs and one output. Now here, it gets a little bit more challenging. So for vector-valued functions, the output are vectors. So what we have to do is we don't plot numbers, which is what we're doing when we're plotting graphs. We have to represent things by vectors. So we're going to do that. Now, on a side note, you'll sometimes hear these referred to as vector fields. So if you hear the word vector field, just think it's a vector function. What we're going to go through is we're going to say, all right, at every single point, I go to that point, and I draw an arrow. And the arrow, well, that's the vector, because we can represent vectors by arrows. That's the vector that corresponds to that point. Now, of course, I should say for every single point is actually a little bit excessive, because if you were to draw it, your paper would be basically black, because you'd be drawing vectors at every single point. You wouldn't be able to see anything. So usually what happens is the they just draw a handful of arrows to help us get a feel for what's happening. Now, one thing to think about is how do you represent magnitude of a vector. So there's two solutions. One is to make sure your vector has the same length at all points. And the other solution is just to say, well, I'll represent magnitude by thickness. Now, for the ones I'm about to draw, I'm going to do them by actually doing length. Or rather, I should say, for the ones I let the computer draw, I'm going to do it by length. Because the computer loves drawing pictures. All right. So here's an example of a vector valued function. On the left-hand side, we have a vector valued function where when you input x and y, the output is the vector x comma y. And if you think about what's happening, it says, look, go to any point. So I come to any point, and it says if I'm at that point, what should happen? Well, my amount of change in the x direction should be x. So I'm changing, whatever x is changing, that's the amount of change I should go. Whatever y is changing, that's the amount of change I should go. And in particular, what happens is that as I come out from the origin, I want to keep moving out from the origin. So if x is positive, the direction of x is still positive, so it's still moving away. If y is positive, the direction of y is still positive. On the other hand, if I come over here, say where x and y are both negative, now I'm moving more negative in both directions. So this is a vector valued function where I can model things by saying, oh, I'm moving out from the origin. And not only am I moving out, but you'll notice that as I move further out, the arrows get longer. Well, that's because the length of the vectors get longer. So in some sense, the further out I go, the faster I want to get away from the origin. Now, of course, we can have more interesting and exotic curves. So here's a vector valued function, f of xy, which the outputs are xy in the x component and x plus y in the y component. And then we have all sorts of arrows going in all sorts of ways. Now, you may have seen things like this before and just not even thought about them in terms of vector valued functions. So if you ever see something that models a flow, so flow can be flow of water, it can also be flow of air. So you'll see this in some wind maps where they're saying, well, where's the wind at? Which way is it blowing? They'll plot lots of individual arrows, and then the arrows indicate the direction of the wind, and the thickness of the arrow indicates the magnitude of the wind. So it's not a bad way to think about things, which is somehow to say these vector fields are representing flows and how things move. In fact, it's such a good way, we're going to talk about this very many times in the future. Of course, this is just one of many. Here's a few more. F of xy equals yx. And you'll see that just a small change here, swapping the coordinates. All right, well, that leads to some interesting different types of behavior. So for instance, in our f of xy equals xy, I'm always moving away. Whereas I have if f of xy is y comma x, you'll see in some directions, for example, along the line y equals minus x, I'm heading towards the origin. In some directions, the line y equals x, I head away from the origin. And then, of course, there's other directions. And again, we're very tempted to just say, follow the arrows. And it's not a bad thing to do. Or you just sort of say, I sort of move in, but then I'm sort of indicating I move out. Now, again, that's not part of the diagram, but it sort of helps us get an idea of how are things flowing through the system. And there's more. You can create these. These are fairly easy to create. So let's try a very special case. Since we're talking about vector valued functions and we're calling them fields, well, a nice thing which is a vector is a force, which means you get force fields. All right. And so let's do force fields. So suppose I have the following. For k greater than 0, so k can just be anything, we're going to try to get a sketch. What does the vector field look like for the function negative k times xi plus yj divided by x squared plus y squared to the 3/2 power? All right. Now the first thing is we should ask, is this in fact a vector valued function? In other words, is this the output of this function, is it a vector? What's the answer? Yeah, it's a vector. Now this is a vector where we use the I and j to indicate what's happening in the different directions. So in essence, another way we could have written this is we could have written it as negative k over x squared plus y squared to the 3/2. And then what we could say is, well, what's attached to the I? That's the x direction. And what's attached to the j? That's the y direction. So x comma y. Okay. So let's think about how we can visualize this. Well, let's think about what's happening. So we pick a point. This is a point. And that's our input. Now our output will be a vector. What can we say about the vector? Which way will it point?
In the direction given to you by your vector there?
Well, that's true. It points in the direction given to the vector. But let's think about where this vector is pointing. Now, do some little scratch work here on the side. If I'm at the point x comma y, if I started at the origin and went to x comma y, that would be a vector that looks like this. Which means, if you think about what's happening here, when we see that we have an x comma y, that means that we're going to be somehow parallel to that direction. So I'm going to be a vector that points somewhere either more out or more in. Now, maybe we should try to answer the question, given that we just said it's some multiple of this, am I going out more or am I going in more? Going in. What gives it away that it's going in? The negative. You see, the fact that I have a negative here indicates that this is the right direction, because it's the reverse of the vector x comma y. So it's a vector that points directly towards the origin. All right. Now we should talk about the length. Now, instead of doing the length of an individual one, we should think about what's happening to the lengths. So for instance, if I were to move closer, say, to that point, so I have 2 points, which vector would have larger length? Now this one's not so obvious. So as you move away, well, let's think about it. What is the magnitude? So if you take the magnitude of this vector, negative k over x squared plus y squared to the 3/2 power, xy, well, the constant comes out, but then we drop the we drop the negative sign. So if we take the magnitude of this, we'd end up with k divided by x squared plus y squared to the 3/2 times the magnitude of the vector x comma y, which is the square root of x squared plus y squared. Now, doing a little bit of cancellation, there's a square root of x squared plus y squared, but there's a lot more x squared plus y squareds downstairs, so we can cancel off a little bit. And indeed, poor planning, but I'll write it as k over x squared plus y squared to the 1/2 quantity squared. Now, you'll agree with me that that's correct. You might disagree in saying, I think you just meant to write to the 1 power. Well, we'll get to that in a second. Okay, so now let's think about it. So, if I'm close to the origin, what's true about x squared plus y squared? It's small. If I'm far, x squared plus y squared is very big. Okay, so now I can say the closer I am, the smaller the term downstairs. The further I am, the larger the term downstairs. So, between these two, which one will have a larger magnitude, bigger magnitude? The one that's closer. So if I'm out here, maybe I have a fairly short magnitude, but if I'm here, a much bigger magnitude. Once you understand these two philosophies, you can get a really decent rough sketch by saying if I'm far, it's a short vector. If I'm closer, it's a slightly longer vector. And however many you feel in the mood for. Whoop. I'm not very good at drawing straight lines toward the origin. That's why we let the computer do the work. Now, of course, you might say, hey, what happens at that point if I have something right next to the origin? Well, or right at the origin maybe. What's true? What should happen?
It's a zero vector?
Well, if I'm at the origin, what's the magnitude?
K over 0.
It's like it's trying to be k over 0. Well, what is that? Well, it's undefined, but it's definitely trying to act like infinity. So what's happening here? It's like there's a hole here. It's like there's a black hole right there. And of course, we can't see it. Or can we? Modern science has something to say about that. All right. So the closer we get, okay, this is a terrible picture. I'm just going to claim I'm going to stop now because I'm not going to make it better. Now, why am I calling this gravity? Because I said gravity. What do we know about the law of gravity? Do you remember what it says? The closer you get to an object, the more pull it has, which is why when you lay down at night, you feel slightly heavier than when you're standing up because you're slightly closer to the center of the earth. Probably not close enough to actually sense it. But what does the gravity actually say? It says that the gravitational pull is inversely, and inversely is just saying 1 over, proportional, that's what constant means, to the square of the distance. That's the distance, and that's the square of it. So this is actually what gravity is. Is this vector valued function? Well, at least I should say it's a vector valued function if we lived in a two-dimensional world, but throw in the third dimension. This is what gravity is. This is how it behaves. So, all right. Now, we have vector valued functions. There's a special case. We say if we have our vector valued function, and it just so happens to be the case that it's a gradient of some other function. So this f here, this is what we would call a scalar valued function, the type of function we've been working with for a long time now. Then we say that the original vector valued function, we call it conservative. And this potential function is this little f. We call that the potential function. Now, how do you think of it? Well, the gradient is something we've talked about before. It's the collection of partial derivatives. So it's not unreasonable to say, oh, the gradient is sort of somehow saying I'm taking a derivative of something and I got this function capital F. So somehow, if we go in reverse, I can say, well, maybe the potential function, I can think of it as some way as the antiderivative of the conservative function. And that's not a bad way to think about it. In fact, it's a really good way to think about it, as we're going to see in the next few lectures. Now, there's a side note here. We've been a little bit spoiled in single variable calculus because we said every function has an antiderivative. But it's not going to be true once we get up into multivariable functions. So when we talk about conservative functions, they're not all vector fields are conservative. So in other words, there's lots and lots of vector valued functions which are not conservative. So this makes things more interesting. We say, well, some vector valued functions are better than other vector valued functions. We strongly are going to prefer the ones which are conservative. Well, how do we find them? There's an easy way to make a conservative vector valued function, which is start with a function you have, a scalar valued function, and take the gradient. So here's an example. Here's a function, capital F of xy, which is some constant k, x squared plus y squared to the negative 1/2. All right. Well, if I want to create a vector field, what do? I find the gradient. So this is a potential function. So the potential function, if I want to find the vector field, I say I take the gradient of that. That will create my conservative vector field. So I'm going to look at the gradient of f. So reminder, that is our collection of partial derivatives. F sub x, f sub y. So let's look at f sub x. What is f sub x? Well, k is a constant. How do you take the derivative of x squared plus y squared to the minus 1/2? It rhymes with train. Chain. Okay, good. All right. We remembered that. Good. Okay. So what does the chain rule say? Bring the negative 1/2 down. And then it's x squared plus y squared to what power? Negative 3/2. Anything else? Times the 2x, times root of the inside with respect to x, comma, what happens for the f sub y? It's almost the same thing. There's one little difference. What's the little difference? It's 2y at the end, yeah, instead of 2x. So, there we go. There's our vector field. Well, let's clean it up. Now, what are some things we can do to clean it up? We can certainly see that there's a 1/2 and a 2 in both entries, and those cancel. We can also pull out what's in common. Well, they both have negatives, so we'll pull out a negative. They both have k's, we'll pull out a k. They both have x squared plus y squared to the negative 3/2. So x squared plus y squared to the negative 3/2. I'll write that as x squared plus y squared to the 3/2. And let's see what didn't get pulled out. What didn't get pulled out from the first entry? X. And from the second? Y. All right. So there's the answer. So there's the vector field that corresponds to the potential function. All right. Well, what's our conclusion? Our conclusion is that gravity, which is a really important thing for us, it's conservative. Now, at this point in previous semesters, we would do some sort of political joke about conservative. However, I've been told I'm not allowed to make any more political jokes. So, all right, so insert your favorite political joke there, and we'll go on. All right. Now, there's one more type of special function which we want to talk about, and that's actually kind of a strange thing to say. It's a function of functions. So what is that? It's called an operator. And so an operator, what you do is you start with a function, you put it into the machine, it changes the function, and out comes a new function. Of course, it was really strange to say a function of functions, so they said we're just going to call it an operator. Now we know examples of operators, and the easiest one that we know is the derivative. So if I start with a function, I can create a new function called the derivative function. Now in this case, we've seen through lots of practice that the derivative gives us insight into what we started with. So in other words, if I know what the derivative was, it gave me an idea of what I can say about what the input was doing. Now, not perfectly. You oftentimes lose information. That's not that unusual to lose something. But the trade-off is pretty good because you also gain information if it's a good operator. Now, we want to create operators for our vector-valued functions. And we're going to do it with what's called del, which we've seen before, the del operator. And we saw this when we talked about gradients. In fact, that's how we're going to start off, by talking about things that we can do. So the del operator, you think of that as the collection of your partial derivatives. Now, it depends on your dimension as to how many. So if we're doing a two-dimensional problem, when we talk about the del, partial x, partial y. If it's three-dimensional, toss in a partial z on the end. But remember, this is really saying I'm taking partial derivatives. There's not a function written down with the del yet, because I'm going to do something to a function. So there's not a function yet. This is going to operate on a function, but we're going to use this to do something. Now, as a reminder, if you ever hear people talk about nabla, that's also another name for that symbol. And just a side note. All right. Well, so we want to make some operators on functions. And these are essentially, if you look at them, these are something to do with vectors. So what we're going to do is we're going to go through our list of vector products. And we're going to say for each vector product, we're going to create something new, some sort of operator. Do you remember what the 3 vector products are? Okay, well, that's good to remind ourselves, because the end of the semester is upon us. In less than a couple of weeks, we have that end of the semester fun part. So the 3 products are, there's the scalar product, when I just scale a vector. The dot product, when I multiply entries together. And the last one, the fun one, is the cross product. So we're going to start off with the scalar product. So the scalar product we've talked about before, that's a good reason for us to start here. That corresponds to what we call the gradient. So what do we do? Well, the gradient says we're going to take a function. It's a scalar valued function, so the type of function we're used to, and it's going to create a vector valued function. Now, for right now, our goal is not to try to say, what does that give us? Our goal is to say, let's practice. We've done a lot of practice with the gradient, but it's good for us to do at least a little bit to remind ourselves of what's happening here. All right, so let's pick a function. Do we want to do a 2-dimensional or a 3-dimensional to start? 2? All right. F of x comma y. So, we need a function. X squared. Do you want more? No. Okay. Well, we'll probably have to do a second one then. All right. So in this case, the gradient of f would be the collection of partial derivatives. So, partial derivative of x squared with respect to x, 2x. Derivative of x squared with respect to y, 0. All right. Well, it's not as bad as the last time I taught the class. Last time I taught the class, they said f of xy is 6. Okay. It is a function. What's the gradient? 0, 0. Yeah. All right. Slightly more interesting. Let's try a 3-dimensional one. This time, let's get even more variables involved. Okay. So f of x, y, z.
E to the arctangent of x, y, z.
E to the x plus arctangent y, z. That's, I think, what I heard. In some sense, e to the power arctangent of x, y, z is actually not hard, but it's not insightful. So I'm not opposed to that. In fact, I am a frequent fan of arctangent, and I've used it before. So we can add a little bit more. Are you satisfied with this? Yes? Always satisfied. All right. Throw something in on the end. Okay. So the gradient of f will be derivative with respect to x, e to the x. Derivative with respect to y. 1 over 1 plus whatever's inside the arctangent squared. Am I done? Times z. I got to do the chain rule. Then I take the derivative of the inside with respect to the variable y. That leaves me with z. All right. Now, is that the whole derivative with respect to y? Yes. Comma. What's the derivative with respect to z? 1. Almost the same thing. 1 over 1 plus yz quantity squared. Anything different? Times y in the end. Okay. All right. I think it's safe to say we probably know gradients. We're pretty comfortable with gradients. Any questions about gradients? Okay. Well, the next product for us to talk about is the dot product. And we're going to call that divergence. So when you hear the term divergence, think dot product. So how does it work? Well, we're going to take the del operator and dot it with f. So I'm going to think of f. Right now, I'm thinking of it here. I've written it as a 3-dimensional vector. It doesn't matter. Dot product works in any dimension. So I have a vector valued function. And when I write this f equals mnp, that really is shorthand. This mnp is shorthand for saying m is some function. And I'm going to think of it as a function of 3 variables. N is some function. So when you see us writing down mnp without writing the vectors, without writing the variables, please know it's just us trying to conserve a little bit of ink. And also trying to get it to fit within the margins we have to work with. So I have this vector valued function, which depends where I'm at. And and I'm going to do del dot f. That's the divergence. So the del operator, remember, is the partial derivatives. And I'm going to dot it with m and p. Now the rule for the dot product is the way you think of it is I multiply the entries together. So when I have partial x and m, well, and it's not quite multiplying, but what I do is I apply that partial x to m. So I get partial m, partial x. The next, I apply partial y to n. Partial n, partial y. Finally, I apply partial z to p. Partial p, partial z. Now, a couple things to note. Once you see this, you say, when I have the divergence, I started with a vector valued function, but I don't end with a vector valued function. I end with just a normal scalar valued function. And if you think about what the dot product did, it did the same thing. It says you start with vectors, you end up with a number. So when we're talking about divergence, we're saying we'll start with a vector valued function, and we end with a scalar valued function, which is just another way of saying a number valued function. Now there's a little comment there. You don't need to know that. But if you're trying to say, well, why do we care about divergence? The idea is that it's roughly trying to measure how much you're expanding or contracting. So that's, in some sense, what divergence is. Again, you don't need to know that right now. For right now, we're just saying, we have this operator. What can we do with it? And this is one way we can think of to work on it. All right, well, let's try it. We have plenty of space and some time. So, what's a nice vector valued function for us to try? It can be a two-dimensional one or a three-dimensional one, whatever you like. Okay, I will give us the first one to get us started, just so we get in the mood for this. All right, so let's do e to the z cubed, arctangent, I love arctangent, y squared, comma, log of x to the 14 plus 2 plus z to the 4, comma, x, y to the power x, y plus z. Now, at this point, you should be getting a little bit nervous and think, I don't think we have that much time left. But I'll tell you, in just a few moments, you're going to say, I love divergence. This is great. Because we like to put problems like this on exams, just to make people start to get a little bit nervous. And then they like, well, okay, got to do it. Let's see where we go. What is the divergence? So del dot f. Well, go to the first entry. Yeah, we're taking it with respect to x. How many x's are there? There's none. 0. Go to the second entry. 0. There's nothing with respect to y. Go to the last entry. 1. So this xy to the power xy, yes, it does create something. But when I'm talking about the divergence, I only care about what's happening with respect to z in that last entry. Which means that at the end, our divergence is 1. These are fun. Now, let's do something slightly more serious. Okay, all right, we've had our fun. Get back to a real type of function. All right, another example.
Cosine of 3x to the z.
Now, we've had cosine 3x to z. Is the to the z power inside of the cosine or outside of the cosine? So is it here or is it here? It does. Because it would be a different function.
I mean, do what you want.
Oh, that's what you mean. All right. All right. Comma. What's the next entry?
Y cubed plus 3.
What?
Y cubed plus 3.
Y cubed plus 3. Somebody likes me. Thank you. Comma.
XYZ.
X, Y, Z. All right. I think that you're going to pretty much agree in the near future, divergence and gradient, they're nice. We still get one more. So, but once you do a couple of these, you're saying, okay, just remember, take the partial derivatives of each entry and make sure you add them up. One of the hardest things is to remember you have to add things together. It's not, you don't create a new vector, you're going to create a sum of terms. Okay, how do you take the derivative of cosine of 3x to the z?
3x to 3zx times, or 3z times x to the z minus 1.
Well, yeah, so you're going to get there. I'm a little bit slower than you, but you are right. What's the root of cosine? Negative sine. Inside stays the same. That's the nice thing about the chain rule. The 3 is 3. And x to the z. So I'm taking it with respect to x. I treat z like a number, which means it's x to a power. Power comes down. And then I subtract 1 from the power. And there you go. That's the first term. Go to the second term. Derivative of y cubed plus 3. 3y squared. The last term. Derivative of xy with respect to z. xy. All right. And so forth and so on. I think divergence, it's not too hard to take divergence of things. So just remember, you take the partial derivatives and you add them all back together, and life is good. Works in a dimension, works for 2-dimensional vector valued functions, 3-dimensional vector valued functions, 17-dimensional vector valued functions, because the dot product works for any dimension. What's left? Cross product. Now, what do we remember about the cross product? What dimension do you have to be in? You have to be in 3. So, this one, we call it the curl. Now, how does it work? Well, you basically think it's going to do what we've talked about. We're going to do something with that operator. We're going to think of it like a vector. We're going to do a vector thing with it. We're going to take del cross f, our vector valued function, and see what we end up with. So we're going to start with the 3D vector valued function, run through it. We should end with the 3D vector valued function, because that's what cross product does. Is it says start with the 3D vector, run it, you end with the 3D vector. So, are there any surprises? Well, not really. Just remember that the curl is the cross product. So we're taking the cross product of these partial derivatives and our vector valued function. And then we get to what I think is one of the most strange things in calculus. We get to take this determinant of this 3 by 3 matrix. And the reason I say it's strange is we think about each row. The top row, I, j, and k, those are all unit vectors. The next row are partial derivatives, and these are all operators. And the last row, m, n, and p, are all functions. So we have this strange mix of vectors and operators and functions. Throw it into a determinant, and out comes something. And the really beautiful thing is it's something that's useful. Now, if you run it through, you get the following. Let's think about what our terms would be. So think about taking the determinant. So I go down the columns, go down diagonals. So in the I direction, I'm going to take partial y of p. So that's where we get the piece of y in the I direction. On the other hand, if we go back in the opposite way, we go I, wrap around, partial z of n. So that's n sub z, but because I went the wrong direction, we subtract. So py minus nz. And you just keep going. J partial z of m. There's your mz. J partial x of p. So that's your minus p sub x. And so forth and so on. Now, if you're going to memorize something, do not memorize the formula at the end. That is a very hard thing to memorize. Remember this formula. That's what you want to remember, because that's going to be the easy one to work with, where you say, okay, set up your determinant, just think of what's going to happen in the process. That being said, next well, not next time, but by the end of the week, I'm going to ask you, does this look familiar? And you're going to say, oh, it does look familiar. And we're going to point to that. But that's coming up by the end of the week. What does curl measure? Essentially, it's measuring the amount of local rotation. How are we turning? All right, so let's do an example. Find the curl for the following. Now, let's be a little bit nice. Curl is already complicated because cross products are already a little bit more subtle. So, nice and gentle, nice and gentle. What is the vector valued function you'd like to consider? In the first entry. What? X? No. No. You're being too nice here. Let's make, I'm going to demonstrate what I mean by too nice. E to the x to the 7. Now, I can get away with this because I know what's about to happen. In a minute, you'll know what's about to happen too. Let's do something nice, but in the y and z kind of thing right now. I mean, not in the y, z entry, just with a nice function of y and z.
Secant of x, y, z.
I don't know if you know what nice means. All right. Y times z, comma. All right, maybe I should just write stuff down. I'm finding that arc secant of y squared plus 1, comma. I'm a professional, don't worry. I wouldn't ask this if I couldn't figure it out. Comma, the last one, e to the z plus log of x plus y plus 1. Something like that. Okay, so there we go. There's our function. We want to find the curl of f, which is del cross f. So we set up our little 3 by 3 matrix. I, j, k, partial x, partial y, partial z. And we write down the entries, e to the x to the 7th plus y times z, x squared plus arc secant, y squared plus 1, and e to the z plus log of x plus y plus 1. All right. And now we're just patient. That's the key. So I come along. I'm going to do my diagonals. I'm always doing diagonals when I'm taking this determinant. I, partial y of e to the z plus log of x plus y plus 1. Well, so I'm taking the derivative with respect to y this last term. The e to the z goes away. Derivative of log of x plus y plus 1 with respect to y is 1 over x plus y plus 1. All right, and that's in the I direction. So that's my first diagonal. Go to the next one. J, partial z of e to the x to the 7th plus yz. Now, so I'm taking derivative with respect to z of that entry. Well, what happens to e to the x to the 7th when I take derivative with respect to z? Goes away. Well, derivative of yz with respect to z. Why? Well, the reason I'm asking is to help us get closer to the answer. Yes, it is y. All right. Plus, okay, k, wrap around, partial x of x squared plus arc secant of y squared plus 1 will become 2x. All right, I've done my downward diagonals in the sort of down to the right. Now I'm going to do down to the left. So I, partial z of x squared plus arc secant of y squared plus 1 is 0. Because there's no z here. So, and that's I, and so subtract 0i. Then I'm going to do j, partial x of e to the z plus log of x plus y plus 1. Well, so I'm taking the derivative with respect to x of that term, 1 over x plus y plus 1. And I subtract. Last thing, k, partial y of e to the x to the 7th plus yz. It's going to be z. And we get the wrong way, so we subtract. And so our final answer is the following. We put everything together. 1 over x plus y plus 1, comma, y minus 1 over x plus y plus 1, comma, zx minus z. So that is our curl. Now, one of the things that you should note is that somehow curl and divergence are kind of opposite of each other. So when we had divergence, we really wanted to have the messy stuff be the non-variable. So if I was in the x entry, oh, put all the crazy stuff in terms of y and z. But here, look at the parts that vanished. That e to the x to the 7th, that arc secant y squared plus 1, that's when the x was the crazy stuff in the x entry. The y was the crazy stuff in the y entry. All right, well, looking at our time, it's a good place for us to pause. Okay, let's do one more thing, because this is just too beautiful not to know. And we'll mention it in passing in a future session. So suppose we have the following. We want to find the curl of the gradient. So essentially what we're doing is we're doing del twice. So remember that the gradient is what? Well, that's del times f, and the curl, so you take del cross whatever you're doing. So we're doing del cross del f. So let's figure this out. So since the curl is involved, that means for sure this is going to be a three-dimensional vector. So we're going to start with our function f. I'm going to say, well, that the gradient of f is going to be the collection of the partial derivatives fx, comma, fy, fz. We'll use subscripts for partial derivatives. Now when we do del cross the gradient, so we're going to have I, j, k of, and then we're going to have our partial derivative operators, partial x, partial y, partial z, and then we have our gradient fx, fy, fz. So what do we get? Well, we get in the I direction partial y of fz. So that we can write as fzy in the I direction. In the j direction, take the derivative with respect to z of f sub x. So that will be fxz in the j direction. K, partial x, f sub y. So that will be fyx, k direction. So we went in our downhill this way, now we're going to go the other direction. So I, wrap around, partial z of f sub y. So that would be fyz, but we subtract because we went the wrong way. J, partial x, fz. So that's minus fzx. J, because we subtract because we're going down the other way. And finally, k, partial y, f sub x. So minus fxy, k. And what do we get? Well, remember that we're dealing with nice functions. And for nice function, the order we take derivatives won't matter. So fzy, fyz, they're the same. But we subtract. So they cancel. 0i. fxz, fzx, same. But subtract. Cancel. 0j. fyx, fxy, cancel. 0k. Meaning we got the 0 vector. So somehow, when we took del cross del f, we're always going to get 0. And notice, this is regardless of what we start with. So for any function f, if we take the gradient, if we take the curl of the gradient, we're always going to get 0. Well, that's interesting. Now, let's switch gears. Divergence of curl. So, what's curl? Del cross our f. So our f, m, and p. And now, what's divergence? Del dot. All right. Cool. We can do that. We can do that. Yeah, sure, no problem. Okay, so what are we going to get? Well, let's work it through. So first off, let's do del cross M, N, P. Well, we could look it up, but we can also just derive it really quick. Okay, I, J, K. Partial X, partial Y, partial Z, M, N, P. Well, what will that be? We're going to get, in the I direction, partial derivative with respect to Y of P. So that's P sub Y. I. J direction, derivative with respect to Z of M. So M, Z, J. K, partial X of N. N sub X, K. So we went downhill, down and to the right. Now we're going to go down to the left, and then we subtract that. I, wrap around, partial Z of N. So that's going to be minus N, Z, I. J, partial X, P, minus P, X, J. And K, partial Y of M, minus M, Y, K. So we get P sub Y minus N sub Z, comma, N sub Z minus P sub X, comma, N sub X minus M sub Y. Okay, so there's the curl. Now remember, we're doing divergence of the curl. So del dot del cross M, N, P will be, well, we're going to come to the first term here, take the derivative with respect to x. So taking the derivative with respect to x, py minus nz. Go to the second term, take the derivative with respect to y. So derivative with respect to y, mz minus px. And we're going to go to our last term and take the derivative with respect to z. Derivative with respect to z and x minus my. So, working it out, we get from the first term, pyx minus nzx. From the next term, mzy minus pxy. From the last one, nxz minus myz. Now, what happens? Well, you might notice pyx and pxy, they cancel. nzx, nxz, cancel. mzy, myz, cancel. What's left? Well, nothing's left. We've canceled everything. And so we got 0. But now it's the 0 number, not the 0 function. Now, you might be saying, whoa, should we have gotten 0 in both cases? And in some sense, you can kind of say, it does make sense that we're getting 0 in both cases. And let me sort of wave my hands a little bit here. Let's think about the cross product. So in the cross product, one of the ideas is that you should be perpendicular to what you started with. So one of the things we start with is del. So the idea is we should be perpendicular to del. And notice that what we're doing here, we're doing del dot. So in some sense, they're sort of like, okay, that makes sense to be perpendicular. Well, does that same thing hold here? Well, what do we know about the cross product? Well, if two vectors are parallel to each other, so in other words, one is a multiple of the other, then they should have no angle between them. So in other words, the cross product should be 0. Well, to be a multiple of each other, it means I just scale by something. So if you think of the gradient as just sort of a scalar multiple of del, so I have del and a multiple of del, well, those would be two vectors pointing in the same direction, so we should get 0. Okay. Now, here's a question. What would happen if you did the following? If you took the divergence of the gradient, is that going to be 0? Well, no. But it is something interesting. So if you work it out, this turns out to be fxx plus fyy plus fzz, and this does have some very interesting applications which show up. So, all right, so amazing properties. And we'll use this next time. And that's it.